You know, all those things that can happen because the ground's moving, all the damages to structures. But you also have other things that can be caused by the earthquake. You can have landslides, episodes of mass wasting. Earthquakes, number one natural trigger of mass wasting events. Many people survive the earthquake, but can be taken out in subsequent landslides and mud flows. You get an interesting phenomenon called liquefaction. That's my personal favorite. And you can also, of course, get tsunami. Tsunami is a harbor wave, that's the translation. And it's often mistranslated as being tidal waves. Tidal waves occur, sometimes monthly or every other month during high tides, and especially if there's a storm system that comes in at the same time, that can produce very high tidal waves. But that happens all the time. Tsunamis are very nasty waves triggered primarily by a sudden motion of the ocean floor, say during an earthquake, or during a sudden displacement of water. Say, for example, you have mass wasting or a volcanic eruption that suddenly dumps several million tons of sediment to the ocean floor. You throw something into the pool, water's going to come out, and that's how you get tsunami. Tsunami for earthquakes typically will not get more than maybe 30, 35 feet high. They kind of have an upper limit on their size. There are limits to how much motion can occur on those faults. Now, the Sumatra quake in 2004 that hit Indonesia, there was about a 90-foot motion on that fault when that earthquake hit. It moved 90 feet. That's why you got a huge wave. People in tsunami don't typically die from drowning. They die from blunt force trauma. They get beaten to death by the other debris that's in the water with them. Not a good way to go. Let's see if I can find the other thing I want to do. Here's. Bear with me. Here somewhere. Grab this thing. There it is. And then there's liquefaction. Faction means to make. We're literally making a liquid. We're taking ground that was originally solid, and we're shaking it, and it's turning into a substance that behaves like a liquid. You can't build structures on a liquid. So when this occurs, many structures that are built on top of it cannot stay up. They collapse. Liquefaction occurs in loose material, especially loose material that's water saturated, like old lake beds or construction fill, landfills, old shorelines, old river valleys, areas where you've had glacial deposits. These materials get full of water, and then when that shakes, those materials get suspended in that water, and they lose all of their ability to support mass, to support weight. A building like this, typically what would happen in liquefaction, the ground underneath would essentially go to quicksand. The weight of the building would squeeze all that stuff out from under it, and then the building would drop into the void, drop into that space below. Buildings aren't typically designed to do that. That would blow these walls out. And if the walls blow out, where's that ceiling going? Down. That's a phenomenon known as pancaking. Yeah, seriously. In Mexico City, 1985, that pancaked a 9-story hospital to less than 4 stories tall. So yeah, they were full. I remember they were rescuing babies out of the maternity ward for about 10 days after that. They were resilient little buggers, I tell you. Many of them lived. There's a picture in your book, classic, 1964 quake in Japan, where they lost several apartment buildings because of liquefaction. And the nice thing about these structures, these buildings were so well built that the buildings themselves suffered very, very little damage. They were just flopped over because the land underneath them just gave out. Let's see, where is that? Is that, yeah, 342. Yeah, 342. These white buildings, those are apartment buildings. They all fell over from liquefaction. And the one that's completely on its side, many of the people that were in that building at the time, they were able to get out of their windows. They were able to walk along that side of the building, and they got down with ladders. They were okay. So the buildings themselves stayed pretty much intact, but the ground underneath them just went kaboom, and out they went. We measure these hazards. We track all of their consequences. Unfortunately, with earthquakes, some of these other things that happen are themselves natural disasters, like the landslides, the liquefaction, the tsunami. The ground motion again, the great gas lines, you can get widespread fires, no drinkable water, broken sewer lines, you get widespread disease. That was a mess. But we measure this. We use the Mercalli intensity scale to measure this stuff. There's a Mercalli scale in your book on page 329. 329. Again, intensities go from Roman numeral I to XII, 1 to 12. The higher up on the list, the worse the damage. So, for example, see, magnitude III, that's a 3. Felt indoors, standing automobile sway, seems as though a heavy truck is passing. So, no big deal. Most people wouldn't even notice that. Then you go up to a 7, VII. Most people frightened and run outside. Not usually a good idea in an earthquake. You can go outside and be absolutely free of any other obstacles. Go for it. But if you run outside, you've got to remember you're going to have power lines and trees and pieces of buildings nearby falling on you from above. So maybe it would just be safer to duck under a table and stay inside until it's over. Frightened around outside, plaster cracks, windows break, chimneys topple, furniture turns over. I mean, you look at an XI, that's an 11. Few masonry, that's brick and cinder block. Well, don't forget this place. Few buildings remain standing. Many bridges collapse. Broad fissures. Big cracks open up in the ground. Pipelines break. Severe liquefaction of sediment. Dams collapse. Facades, all your decorative stuff on buildings, collapse and fall off or are severely damaged. And then you go to a 12, and there is nothing left. That's 12. How do we get these values? How do we get this information? Well, shortly after the quake, there are going to be all kinds of people in the field. There are going to be rescue teams, there are going to be engineers looking for damage, looking for unsafe buildings and structures that need to be condemned to make sure that people stay out of them so they don't get re-injured. They'll be keeping track of what types of damages they see and where they've seen them and what types of structures. So we'll be getting information from that. Darn skippy seismologists and geologists are going to be crawling all over this place as soon as the tops will let us in there. And we'll be looking for specific types of damage as well as getting information. In the days after the quake, there'll be volunteers. They're actually a standardized questionnaire. And they'll be going to people who experienced the quake and asking them questions from that questionnaire. Did you hear car alarms go off? Did you see trees sway? Did it wake you up? And they'll be asking them questions to try to get their real-time experience of what they felt during it happened. The whole point is because we want to map these intensity patterns. And there is an intensity map also on page 329 for Charleston, South Carolina. It has different intensities. And Ohio, we're mostly in green. That's intensity 5. So, South Carolina, there are some huge faults just offshore. And those faults are there from way, way back when, 200-some million years ago, when Africa separated from us to open the Atlantic. And when continents pull apart, when there's rifting, that produces normal faults. and those are still active periodically. Biggest problem with earthquakes in Charleston, South Carolina, is that they're so doggone flat there that earthquakes can cause massive landslides into the ocean, and they have super threat for tsunami because of that. So we get another big one in South Carolina, big one being probably about an 8 or so. We have the largest historical quake in the southeast that occurred in the 1880s. Killed 100 people. That's not bad for, not that many people living there. So Ohio is just up from that in intensity 5. So the next big quake in Charleston, South Carolina, what are we going to experience? Most people will be woke up, dishes and windows break, unstable objects tip over, trees and poles sway, and we'll feel that here, all the way from South Carolina. It's quite a distance. That energy travels throughout the whole Earth. We'll want to make smaller scale maps as well, especially of the region in question. So say, for example, here was your quake, and you'll map those intensities, and here was a 10, and then maybe there was a 9 around that, and then maybe there's an 8 around that. Then maybe over here, there's a 1. And maybe over on this side, you have more solid bedrock, so the waves go in and out and through very fast, and they'll cause a lot of damage. But maybe over here you have maybe an old lake bed or some wet glacial deposits, and so you get a lot of liquefaction. It shook more. City planners are going to want to see maps like this so they can plan ahead. We're not to put the new trauma center hospital. We're not to put the new gas pipeline. We're not to put the new high school. Definitely they're going to want to look at it to see if they need to revise building codes or zoning restrictions. Hazard management departments are going to want to look at this so they can make better plans for the future, to be better prepared for the next quake. Insurance companies are going to want to see these maps so that after the quake, when you're on the phone to Nationwide, Prudential, to State Farm, and you're saying, oh, my house is gone, it's a total loss, we've lost everything, the chimney's all in the backyard, and oh, there's a collapse, the tree fell in the car is gone, and we don't have anywhere to stay, and the second story's in the basement, and like, oh my gosh, where do you live again? What's your address? Oh, we're at 33 Elm. 33 Elm, yeah. And the house is gone. Oh, it's completely gone. The cars too. They're completely destroyed. Really, 33 Elm. That street? Yes. 3. See, 3. Skeleton doors. Automobile sway. Seems as though a heavy truck has passed. Really, the house is gone. Oh yeah, it's gone. Yeah. We'll send an insurance adjuster out there as soon as we can to take a look and assess the damage. Yeah. This little thing called insurance fraud. And these types of maps help to curb that. Now, true, something really bad is going to happen on Elm Street. Perhaps you had an old, aging water main that broke, just enough shaking to break it, and maybe that's washed dirt and sand and soil out from underneath the house, and that's how the house is collapsed. Who knows? There are special circumstances. So that's definitely a claim they're going to want to investigate more closely. And they're also going to look at that and say, okay, well, these people here don't need as much coverage, but these people, we've got to up our policies in this area for people to have earthquake insurance. Like any natural disaster, earthquake insurance will be a separate policy, be a separate rider. You can get earthquake insurance in the state of Ohio. I don't know. The kind of shaking we get and the odds of it happening are very slim. We do have faults in Ohio. Most of these faults are left over from the building of the Appalachian Mountains, which occurred and was completed by about 250 million years ago. There are some faults up by the Pennsylvania border in northeastern Ohio. There are some faults near the Indiana-Kentucky border in extreme southwestern Ohio. And there are some faults that are north of us, outside of Anna, in Shelby County, that are also periodically active. These are all very old faults. They're associated with very ancient plate tectonics that's no longer active, and hasn't been for a long time. But there's still areas where rocks are broken. And like an old house periodically settling on its foundation, Periodically, those broken areas, they shift and move, and we feel that as minor earthquakes. Those earthquakes in Ohio, they're capable of generating quakes as high as maybe a 5.5 or 6 on a magnitude scale, but typically they're less than 4 and less than 3. They're little microquakes. We do have a much larger ancient earthquake zone, sort of to the south of us, down the Mississippi River Valley. Parts of it extend into the border between Indiana and Illinois. And this region here, okay, you're here, that's Sadie right there. You are here. And our earthquake zone is here. It's called the New Madrid Fault Zone. And for reasons that we don't quite fully understand yet in science, back about 1.5 billion years ago, our continent started to open, began divergent continental rifting in that area. Just started to open up like a zipper, and then it stopped. But that opening, the evidence of that opening is still there. All the rocks there are broken badly. And now, 1 billion years later, those broken rocks are buried under miles thick of heavy sediment. So periodically, they shift and move under the weight of that sediment material. That whole zone is lined front to back with recording equipment, and they record almost continuous activity in that region every day. Mostly microquakes, again, quakes that are too small to be felt by people. They're only detectable by machine. 1811, 1812, some of the world's greatest earthquakes occurred on that fault. Estimated magnitudes in the 9.6 to 9.8 range. Massive. In 1812, they killed several hundred people, and there is a threat that it could happen again. That happens in modern times, where we're sunk. Absolutely, that could easily collapse our entire national economy. A lot more things there, from St. Louis to Little Rock to Memphis, can be impacted. We'd be impacted greatly. But we may have dodged a bullet. Recent research suggests that the stress that accumulated there to cause those massive earthquakes in the 1800s, the cause of that stress was from the building of the Appalachian Mountains. Well, those mountains are done. I mean, they're in retirement, being Walmart greeters right now. They're done. So there is no source for the stress. The source of the stress is not there anymore. So it's not capable for the faults in that New Madrid region to accumulate enough stress to produce earthquakes of that size anymore. That's what the new data shows. We're hoping you're right. Any questions? Yes?
Since we're at 5, I think that we're kind of like in the middle of it, right?
For what?
For the scale?
For which scale? Intensity or magnitude? Intensity? It just means that our damages, our observed damages, will be light to moderate.
So if we had an earthquake here, like, how far away would you be able to feel it?
There has been magnitudes 3, maybe between 3 and 4, that have occurred in southern Indiana near Evansville, which is in southern Indiana near the Kentucky border. It's in that part of Indiana. And you feel near downtown. Yeah. Rocks in the central Midwest and the eastern Midwest tend to be rather flat, so they transmit that energy rather easily and rather quickly. So we would definitely, if there was a quake, say magnitude 6 or 7 in the St. Louis, Memphis area, we'd feel it here. Yeah. But most quakes that occur west of us, like on the Pacific coast, California, through the mountains and the Rockies, we don't feel them because the Rocky Mountains tend to absorb a lot of that energy. And by the time it gets to us, it's so weak that it would be something detectable by equipment, but it's not something that in our daily lives we would notice. Does that answer your question? And of course, Charleston, South Carolina, they have a big quake. We'll feel that impact here, and they will likely get tsunami. But that tsunami won't impact us because we have 2,000 feet of mountain between us and that. Tiles look a little better every day, just a little. Any other questions? Yeah.
In the, I think it was late 70s, early 80s, I remember feeling, was that from the South Carolina?
No, those were, and I remember feeling it too. I remember my dad was at the table reading a newspaper, and he had a glass of lemonade, and the lemonade glass was just bouncing across the table, and he's like, what the hell is going on? We did have some paranormal activity in the house I grew up in. Occasionally did nothing, nothing really creepy, but it is what he thought it was. He thought it was, Ed, you messing with me again? But no, it was an earthquake. Yeah, I was on the floor. I could feel it through the floor. Those were out of the Shelby County area. Yeah. Any other questions? We get them more often than you think we do around here, but again, they're so weak we usually don't feel or don't notice them. Between driving and walking back and forth, you don't notice it. Any other questions?
When was the last one you had?
Last one that we felt here, that I remember maybe a couple years ago. And Cheryl, I felt that I was in my truck. That's about 3 years ago. I had a truck then, and I was parked at a stoplight, and I could feel it. Sometimes you bring the car to a stop, and it still kind of feels like it's still moving. You ever had that? It's like, oh, wait, stop. But I could feel it kind of bouncing back and forth a little bit. I thought it was the wind, but then I got here, and everyone, did you feel the earthquake? I'm like, damn, it's an earthquake, shoot. I was down by the river. I was off of Stewart Street, so liquefaction. I was catching that swarmy motion from the center underneath, and I missed it. So, any questions? So, where do we typically get earthquakes? Earthquakes occur on faults. Faults start with the breaking of rocks, and then the rocks move along that point of breakage. So, definitely, earthquakes are related to plate tectonics. Start with a couple easy ones first. We've got hot spots. We'll start with hot spots and transform boundaries. Hot spots is a small localized region where you have a concentrated jet or plume of hot material coming up from below. So that's going to be pushing its way up to the surface, so you'll get compression pushing up from below. And as that lifts the crust above it, the crust above will stretch and break apart. So you get compression from below and tension across the top. At hot spots, you'll get the development of both normal and reverse faults. And these will tend to produce shallow quakes. Typically less than 40 miles in depth. Less than 40 miles. The quakes will usually be associated, or I should say frequently, be associated with the motion of that hot material towards the surface. So in hot spots, earthquakes, even though they can be problematic and cause damage, injury, and death on their own, they can also be a useful indicator that volcanism is about ready to happen. So they can be a good predictive tool to help give some warning for an upcoming volcanic eruption. And then transform. What kind of plate motion do we have at transform boundaries? How are the plates moving?
Sliding.
Side to side. This is going to give us what type of stress? Shear stress. What kind of fault is that going to make? Strike slip. Again, these tend to produce shallow quakes, less than 40 miles deep, shallow focus. Sometimes the foci of these earthquakes can be at the surface. They can be less than 5 miles deep. And that can make them very disastrous because then most of their energy goes to the surface where we are. San Andreas Fault System is related to a transform plate boundary between our west coast and the Pacific Ocean. That triggers a lot of nasty earthquakes. Transform plate boundaries can produce big ones, definitely easily 7 to 8 to 9 in magnitude. We have other places around the world that have issues with transform boundaries. We have Turkey. Turkey's this little country in here. It's got 2 transform boundaries, one across the north, the one across the south. It's like nobody wants Turkey, so they're trying to pinch it out into the Mediterranean. It's like, get out of here. You know, say, pinch. And they get nasty quakes, nasty, easily 7 to 8 magnitude. And it can cause massive destruction. Many places throughout Turkey have very poor people. They have very low economy. They don't have a structured government in the sense that they don't have a lot of the support systems that we do. If something happens, yeah, sure, you know, Red Cross and Red Crescent will come in and help, but they don't have access to a lot of insurance to cover damages. The places they work at, the businesses they work at, don't typically have insurance to help them through disasters. They don't have a lot of federal assistance to help them out. So the consequences of a big quake in regions like Turkey can literally last for decades and have long-term consequences. August 30th, 1999, there was a major quake in northern Turkey on one of those transform boundaries. And in the 10 years after that quake, their national suicide rate went up by more than 300%. Because even 10 years after the quake, there's still so many people without a home, without a permanent home, without a job, they had literally lost everything. It's just a depression. Their suicide rates went up. Let's see, what else we got? We look at divergent boundaries. How do plates move on a divergent boundary?
Away.
They separate, they move away from each other. What stress is that? That's tension, pulling apart. Tension stress gives us normal faults. And again, this will produce typically shallow quakes, less than about 40 miles. Don't really know about most of these quakes because they occur on divergent boundaries. Most of our divergent boundaries are on the ocean floor. We don't have anybody living there yet. So, they're 5 miles deep of water in the middle of nowhere. You don't feel them. Typically, they'll be most commonly in the 4 to 5 magnitude range. Sometimes you can get a 6 going out there. We do have other areas like our New Madrid. That's an old divergent boundary. We also have here in East Africa, the East Africa Rift. Here, that's a divergent boundary. They get some good-sized quakes there every now and then. The population density isn't as high in that part of the world as it is elsewhere. So when they do have major quakes, it usually doesn't impact a lot of people. So that's a good thing. And then we have the convergent boundary. How do plates move at convergent boundary? Towards each other. What stress does that produce? It's going one way. Compression, squeezing. Compression stress is going to give us reverse and thrust faults. at subduction, we have our ocean plate going underneath our continent. How many times have I put that on the board? If I had $1 every time I do that on the board since I've been here, I would leave this job. Always have to remember that when you see drawings, either these fabulous artistic renditions that I do, or better ones that are in your book or on the internet, they're drawn for simplicity. But in reality, you're dealing with rock. Okay? What looks like nice, even lines on the drawing are not in real life. They're rock, they're jagged, they're broken. That subducting plate doesn't just whoop into the mantle. It periodically is going to get caught and snagged on the underside of that socket. You get pokey out parts and pokey in parts, and they catch each other as when they try to compass. So you'll get little jerking and starting and stopping and popping and snapping all the way down. And 1960s, 1970s, this was discovered. You'll have earthquakes that can occur all along this zone of subduction, down to about a depth of 300 miles, all along that place. Down around 300 miles or so, and that's a ballpark. Some places it's less, some places it's deeper. But what happens, the deeper you go into the earth, it gets what? Hotter. That heat melts the rocks, makes them soft and gooey. So if the rocks are broken and they get soft or melted, they flow back together again across the point of breakage. So that break heals. Without the break, we have no earthquake. So they can only exist to that depth of melting. But all along that subducting plate will have these earthquakes. You'll produce shallow quakes near the coast. You'll get medium deep quakes further inland. And you'll get very deep quakes farther in. That pattern of increasing earthquake depth is called, named after the guy that discovered it, it's called a Benioff zone. Can't remember his first name. And in the 90s, it was discovered that another researcher around about the same time had also discovered this, but had never been credited. So now his name is on here too, and it's the Wadati-Benioff or Benioff-Wadati zone. So I don't get credit. These quakes can easily be magnitude 6 and higher. It's going to be nasty. The earthquake that recently hit Japan, probably that's been like almost 2.5 years ago now. Can you believe that? It caused that big tsunami in Japan. That was on the subduction zone. That is a special case of subduction, which occurs because the rocks are not smooth. Get your plate going down this way, and then that's curve right there. What can happen is that subducting plate can catch the edge of that continent, can grab it and snag on it, and pull it down in with it. So gravity pulls that in with it. Continental crust doesn't want to subduct. Doesn't want to go down, it wants to go up. So what's going to happen to that when that breaks loose? It's going to snap back. It's going to snap back out. And this breaks free, and this will pop back out and come back out again. Well, that snaps back. What's out here? Water. What happens when you slap the water? You slap the water comes out. This snaps back, and the water, and you get tsunami. This could be a huge tsunami generator. And if it's close to shore, you may have less than a minute warning that you have tsunami coming. Head for the hills. Any questions?
No,
Yes.
I struggle with hot spots. What kind of stress is that?
Well, you get a mix of compression from below and tension across the top.
Okay.
Yeah, you think of it like a chocolate bar, like a Snickers or a Milky Way. How would that be good right now? So you got like a Milky Way, and you're holding the bar, and you're pushing on it from below with your thumbs to bend it. As you push up from below, what happens to the chocolate on the top? It cracks because it's stretching across the top. So you get compression from below and tension across the top. Yeah. Do that this next week with Halloween. You're giving out the candy. You go, oh yeah, yeah. Did it on that one too. Yeah. That's abduction. We can also get collision, continents hitting each other in convergent tectonics. When you get continental collision, you're going to build very tall mountains, and you're going to also build a very deep mountain root. Definitely cause some broken rocks to develop. You'll get reverse and thrust faults. And they can shift and move, and you'll get medium to deep quakes. Some of them can be quite substantial. Easily 7 to 8 magnitude range or higher. Definitely. India, northern India, Mongolia, Pakistan, Afghanistan, Iran, Iraq, they get these types of quakes. Back in the early 90s, there was a very large, it's like a 7-point-something quake in northern India near their border with Pakistan. And several thousand people died, mostly because they're at higher elevation than we are. And even though it was near a modern city, at those elevations, with no electricity, no gas, they didn't have any heat. And many people died of hypothermia and exposure to the elements before they could be rescued. They were desperate for heavy machinery, waiting, because you got to wait a little while for rescue teams to fly in from other nations to help out. And the only thing they could find was this old beat-up steam shovel. And they were trying to use it to help lift pieces of buildings and rubble off the people to try to rescue them. And they actually broke it trying to do that. Now again, that speaks to the economy of the region. Think of just Dayton. We have at least 7 active quarries within 30 miles of Dayton. We could have bulldozers and heavy machinery here in an instant. In fact, we wouldn't even have to go that far. They're building 75 just down the street. We have all kinds of cranes and heavy machinery. We got Wright-Patterson Air Force Base. They would have machinery and supplies and lighting and manpower. So it depends a lot on your economic status and your culture and what you have available to you. Yes?
To go back to the one that caused the tsunamis real quick. If there's a big enough tsunami and there's like volcanoes right next to the water, how does that exactly like affect the volcano?
It doesn't.
It doesn't at all?
No. Because typically the volcanic mountains produced by subduction will be easily more than 10,000 feet tall. And your tsunami is only going to be maybe 35 feet. Yeah. The volcanoes don't even know they're there. Now you can have one of those volcanoes actively erupting when the earthquake occurs and tsunami happens. Which is rare. You get that many natural disasters at once, but it does occasionally happen. Yeah. But as far as impacting the actual volcano itself, no. It could cause a substantial enough earthquake. It may cause enough shifting underground that could maybe reactivate one of those volcanoes and make it more likely to have a future eruption. But it's going to take a while for that molten material to come up. Does that answer your question?
So, like, if there's like a volcano, like really big at the edge, like into the ocean, and there's subduction and that vibration underneath the water,
Yeah.
will it like have any kind of impact on the volcanoes since there's like the vibrations going on?
I mean, it will shake. You might get landslides off of it. Yeah. But you're not going to get a volcano exactly at the coast unless it's hot spot. Subduction, because you got to get that plate deep enough so it will melt and have the melted stuff come up. So your subduction volcanoes are going to be inland a little bit because they have to be where that subducting plate's deep enough to give them the magma they need. Now, you see, in May of 1960 in Chile, they had like a 9.3 quake on Saturday, and then they had a 9.6 on Sunday. And those two quakes, they caused massive tsunami that took out the entire coastline of Chile, killed several people in Hawaii, killed over 100 people a day later in Japan. The earthquake triggered huge mass wasting in the Chilean Andes mountains that dammed a river to a point where the river almost burst through its banks and caused devastating flooding. They had to dig out the debris of the landslides and let the water out. It caused massive fires, forest fires, because one of the volcanoes erupted also. And they had, and then they had torrential rainfall for about 6 days that created mud flows in the mountain. That was not a good weekend. And many people died, more than 5,000 people died. And in May, because Chile is a country in South America that's south of the equator. So May is actually their winter. It's the beginning of their winter. So many people died of exposure to the elements. They can get massive. They had one not too long ago in Chile, subduction. That was off of near the capital of Santiago, not too long ago, a couple months ago. They had a massive quake with tsunami. Any questions? Good grief, an earthquake will definitely ruin your day. For sure. It's kind of nice if you knew in advance when one was coming. I mean, we at least can track bad weather and know, oh my gosh, there may be a tornado coming. Okay, well, you get the kids, I'll get the dog, and we'll get the basement. It'd be nice if we could have some kind of warning for earthquakes. So let's look at earthquake prediction. In earthquake prediction, what scientists are looking for mostly are something called precursors. Things that happen before the quake. Little hints or suggestions that tip us off, give us a clue that something else is coming. There are many kinds of phenomena and things that have been observed to occur before a quake. And scientists, seismologists keep track of all this stuff. We have foreshocks, we have changes in electrical and magnetic properties of rock. We'll get changes in the surface of the ground, so changes in ground elevation. Ground will shift, it will bulge upward or drop down or shift sideways, it will move in unexpected ways. You can also get changes in the water level in wells. So you get changes in gases coming out of wells. We we get really weird animal behavior. Keep track of all this stuff. Foreshocks. Foreshocks are smaller earthquakes that occur before the big one, before the main quake. And it goes back to what an earthquake is. It is the release of accumulated stress. It's where rocks on a fault break loose of each other. So as that stress is accumulating and that's trying to move and it can't because it's stuck, areas that are weaker are going to start to break first. Now, when these little areas start to break, that means that the big place where it's caught is under even more stress. It's kind of like if you're helping somebody move something heavy, like move a case freezer or move a big heavy dresser drawers or a big couch, and you're trying to hold your end and they're trying to hold their end, and all of a sudden they're like, I don't got it, I can't, I'm moving, I got it. Then it's up to you to try to hold the whole thing before it goes rolling back down the stairs. Yeah? Okay. Well, that's what a foreshock is. It's the weaker areas on the fault that are starting to give way and break free before the main quake. But it can be very difficult to tell if that's a foreshock or if it is the quake. That 1960 quake in Chile, the quake on Saturday, it was the foreshock. Okay. Yeah, the quake that happened on Sunday, the day after, was the main shock. And they had smaller quakes after that for over a year. Yes?
If you have enough like smaller foreshocks, is it possible that those could eliminate the danger of a larger earthquake?
Well, because you may have a foreshock that may be a magnitude 4, and that may be preceding a main quake of magnitude 7. Remember, each one up on the magnitude scale is 30 times the energy. So a 7 would be what, 30, 900, 2700 times as much energy as the 4. So, no. Because it's not going to release it, it's going to build the energy. Because that little part is helping hold it together. If it goes, then it's all for that big part to hold it all. So that actually makes it worse. Right?
Can you have multiple foreshocks before you have the actual?
Oh, yeah. Yeah, you can have foreshocks for days or weeks. Yeah. Sometimes. Not always, but sometimes, yeah. We can change electrical and magnetic properties of rocks because when we measure those, we measure the magnetism of the rocks, we can measure their conductivity to electrical. We can see the changes in water levels. Think of what happens when you squeeze a sponge. You squeeze the sponge, the water comes out. You let go of the sponge, the water goes back in. You squeeze the rock, water and gas come out. You let go, water and gas go back in. So when we see these changes in wells, higher levels of radon gas, methane gas coming out of wells, water levels coming up and down in wells, again, that's telling us that there are changes in stress happening underground. There may be areas that are getting ready to break loose. The stress is changing, it's shifting. You get changes in ground elevation. Many major faults in this country, especially the San Andreas, we have for decades, for well over 40 years now since the technology came out. We have lasers that shoot across the fault. They can stay straight for several miles, which, because it's light, right? And light isn't affected by gravity as much, or the same way, say, a projectile is, which always bothered me about like Star Wars. How can you not hit somebody with a laser gun? Okay, it's not like you're shooting a bullet, the bullet's going to go out and start falling. So you got to compensate for distance and wind direction and all that. It's pretty much where you use a flashlight, where you point it, that's where it's going to go. I don't understand that. But we can measure with those lasers changes in ground elevation and motion to within fractions of a fraction of an inch.